All right, here we are. All right, so we're getting ready to get back into number 6, chapter 6. And here we go. Hello. Yeah, so chapter 6 today. We just started it, just barely started it. We'll just carry on with it today. And again, as usual, some of this material might be familiar to you, and some of it might not be. So, okay. Oh, hold on one second. I have to go get something out of the other room. All right, I'm back. All right, here we go. So let's get chapter 6 open, and we can get started. Another exciting week. I don't know. I think eventually there might be a day off this month. It is March now, and instead of a spring break, there's 1 or 2 days that are just off for no particular reason. I don't remember what days they were, though. You may have it written down in your calendar somewhere. I don't think any of them happen this week, but I think that at some point this month, you may actually have 1 or 2 days off. They made up some name for them or other. In fact, just to make sure, let's go look at the calendar for a second. All right, here we go. Assuming this is the most updated version, you've got Tuesday the 23rd, Wednesday the 14th. Oh, so this is not even close. Monday the 3rd. All right, so I just thought you might want to be reminded of that. I remembered it was March. I just couldn't remember when in March that the first one will take place. So it doesn't even have a name of a holiday here. It's just like, well, you kind of deserve a day off. So here you go. And so those are the ones that take the place, of course, of the spring break, which we normally would be having. There you go. You see how that works? How infuriating. But you might have a class on Wednesday or Monday. So that's right. So that's how it works now. Spring break is it's an archaic thing of the past. No. By this time next year, I'm sure, by this time next year, we might be back to normal. We will see about that. All right, anyway, let's get this going. So we're looking at spring. Hold on 1 second. Yeah, so I know we were definitely in the middle of linear inequalities. So let's take a look at that. Oops. All right. Okay, here we go. Let me just save this real fast. All right, so we've done some evaluations of algebraic expressions. We've also been solving for them. We've been going through some important definitions. We solve for linear equations. And then we just barely started talking about inequalities. Okay, so I just want to remind you that there's 4 different ways this can happen. We could have strict inequality like we do here. This one is inequality, which allows for the possibility that the number is 0 or negative. Here we have strict equality, strict inequality again, because it's greater than, and then here this one allows for 0. So in terms of terminology, a number which is definitely less than 0, strictly less than 0, is said to be negative. But if we allow for the possibility of equaling 0, then we will call this number non-positive. Okay, in other words, it's either negative or 0. Rather than having to say negative or 0, we call it non-positive, because the only thing that's disallowed is positive numbers. Now here it's the other way around. If x is strictly greater than 0, then we call x positive. But if it is greater than or possibly equal to 0, then we call it non-negative. Okay, which means that the only thing that's disallowed is a negative number. Okay, now with an inequality, what we're going to find is that the solution is not a single number, but a set, an infinite set, as it turns out. For example, here, if this is your inequality, then that means all real numbers 7 or below are going to belong to the solution of this inequality. Okay, so like you saw before with equalities, linear equalities, sorry, something like this, if I have a straight line, y equals, let's say, 3 plus 2x, then this is what I'm looking for. This is my solution. Whatever the value of x is, that's the solution, because at this point, this is the value of x. At which y equals 0. And that's what it means to be a solution. But when it comes to inequalities, then you've got, instead of a single value, you've got a whole slew of values. In other words, you've got an infinite number of possibilities. So if we try something like this, that x is less than or equal to 7, this is the line x equals 7. So that means everything to the left of that satisfies the inequality x less than or equal to 7. So that's one of the big differences between these two, equalities and inequalities. With an inequality, you're including an infinite number of possibilities. So over here, it's just a single value. Okay. So over here, we have linear equality. And over here, we have a linear inequality. Now, of course, the one on the left, this is the one we use the most often. I mean, this is by far the more useful of the two. In practice, if you wanted to know, for example, imagine you're running a business and you want to figure out how many units of my product should I sell to make the most profit. It's not going to help you very much to be told that anything above 50 is fine. Well, I know I need a number. I need a single value that will tell me where am I maximizing my profits. So the one on the left is more useful, but we do run into the one on the right under certain conditions. So one of the things we have to watch out for, though, when solving these linear inequalities is that, well, we'll see it when we get to that point, but the rules are slightly different. In other words, when we algebraically manipulate an inequality to solve for it, there's one thing we have to watch out for, and you'll see that when we get to it. So we, of course, will, as we always would with any other equality we've ever seen, we could potentially use addition or subtraction or multiplication or division. So here's a perfect example of this. If a is strictly less than b, if I add the same constant to both sides of that equation, I haven't changed anything. So this statement is still true. And if I add a negative constant to both sides, I still haven't changed anything. So this statement is still true. Now, that was also true, if you recall, with the qualities. If I had, for example, a equals b, then it must be the case that a plus c also equals b plus c, and a minus c equals b minus c. So that hasn't changed. This was true for equalities, and it's also true for inequalities. The question now is what's different between equalities and inequalities? Well, let's find out. Okay, so what about multiplication and division? What if I have A is less than B? If I multiply both sides by C or divide both sides by C, I'll have the same, or the statement will still be valid as long as C is positive. That's the key right there. Now, with equalities, that isn't necessarily true. In other words, if I have A equals B, and I decide to multiply both sides by negative C, nothing's changed. It's still a valid statement. But when it comes to inequalities, that's no longer true. In other words, if we're multiplying or dividing by a negative number, then something does change. And that is something unique to inequalities. So what is it that's different now? What's different is that the sign changes when I multiply or divide by a negative number. So in other words, let me show you some numerical examples here. So in other words, suppose I say that A is less than B, CA is less than CB. So if I have numbers like 3 is less than 7, if I multiply both sides by 2, this is still valid, isn't it? But what if I multiply both sides by negative 2? It's no longer true, is it? Ooh, what happened here? No, that we have to reverse the direction of the inequality. Look. Okay, so in other words, I've multiplied both sides by the same negative number here, but now that would be no longer a valid statement unless I reverse the direction of the inequality. Otherwise, you've changed something. All right, so in other words, here you notice I started with A is less than B. I multiply both sides by positive 2, and nothing's changed. I'm fine. But when I multiply both sides by negative 2, I have to change the direction of that inequality because otherwise I now have an invalid statement. This is something that did not happen with equalities, of course. If I had something like this going on, well, instead of using numbers here, I'll use letters again. Otherwise, it's going to look a little ridiculous, but no, maybe not. Let's do this. How about if I start with 3 equals 3? If I multiply both sides by 2, this is certainly still true. And if I multiply both sides by negative 2, this is still true. Okay, so with equalities, multiplying and dividing by negative numbers, not a problem. With inequalities, it's okay as long as you remember to reverse the direction of that inequality. All right, so this is for both multiplication and division. Why don't we show that with an example? If I had, instead of 3 and 7, I had something like this, 4 less than 8. Now again, if I multiply both sides, let's say instead of multiplying, I divide, okay? 4 over 2 is less than 8 over 2 because this is the same thing as 2 less than 4. But if I divide it by negative 2, I have to change that direction because now we're comparing negative 2 to negative 4. And on the real number line, of course, if you recall, once we get into the negative territory, negative 2 comes before negative 4. So negative 2 is greater than negative 4. Even though 2 is less than 4, negative 2 is greater than negative 4. So dividing by negatives means we have to reverse the direction of that inequality. Okay, multiplying and dividing by negative numbers means we must reverse the direction of the inequality. That's the only thing you have to worry about, though. Otherwise, when you're dealing with inequalities, you can solve them any way you like, as long as you remember about this little problem here. So in other words, when dealing with inequalities you must reverse the direction, we'll call it, of the inequality when multiplying or dividing by a negative number. All right, if you remember that, you're good. All right, otherwise everything's the same as when you're dealing with equalities. That and the fact that with inequalities, you're going to get an infinite number of solutions. All right, so I'm sure you knew that at one time and you may have forgotten it, but now it's back in your memory. So here's an example. It's an inequality and it's pretty straightforward. Let's solve for this inequality. Add 7 to both sides, as we always do. Divide out by 2 and we're all set. Well, that was easy. But remember too, like I said before, this means that you're including everything below. Or what you could do is look at this on the real number line and just say anything under 8 qualifies as a solution. It's an infinite number of possibilities. But the next one, no, the next one will be different. Don't worry. We do need some practice where we have to worry about changing the direction. All right, are we ready? Yeah, let's look at this one. Okay, so this time, remember, we're trying to isolate not negative x on one side of the inequality, but x. So we're going to start by multiplying both sides by -1. And that means this greater than or equal to becomes less than or equal to. Okay, now it's a little bit easier because you can just add 5 to both sides and then just divide out the 4. And this means we have less than or equal to 3. Now, if you want to double check, it's easy. You can literally plug any number less than or equal to 3 into this original inequality, and you'll see that it does in fact work. So let's try 0. 0 is less than or equal to 3, so watch. And yes, this is a valid statement. All right, so we got one more here. I think it's just one more. Yeah, maybe we could do a few more. I'll make up a few just to make sure we're getting it. Okay, how about this one? Now, in this case, what I did was I noticed, and it doesn't, you don't have to do it this way, but I noticed right away that they all have a common factor of 25. So I just speeded things up a little bit by dividing out both sides by 25. And then, of course, it's easy because you can add 3 to both sides. We did not at any point here, though, have to change the direction of the inequality. And so we can once again confirm this with our double check. Let's try 10. Anything above 7, remember, qualifies here. Oh, wait, I'm copying the wrong thing, sorry. 25 times 10 minus 75 should be greater than or equal to 100. 250 minus 75 is greater than or equal to 100. Yes, 175 is definitely greater than or equal to 100. So that means we've done this correctly. All right. So let me just make up a few new ones so we can get some more practice. Or more practice is always good, as you know, like anything you do. It's not just math. If you're doing piano, well, you know what I mean. Those fingers have got to be on those keys every day, don't they? Oh, yes. All right. Let's try this one. All right. Once you come up with the inequality for that one, I don't know what the answer is because I just made it up. All right. So we can start by simply subtracting off the 4. Now, normally with inequality, you would just divide out the -2, and that would be the right thing to do. But now here's the thing. You've got to make sure that you reverse the inequality because you've divided by a negative number. If you forgot, you'd have it exactly backwards. So let's double check. We'll try -3, let's say. Okay, so -3 is +6. And yes, this is a valid statement, so therefore this is correct. All right, I hope you got that right. That was the key right there. Reverse the sign of the inequality because you're dividing by -2. All right, let me make up another one here. And then we can go on to something else. All right, why don't you take a minute and look at that one? All right, I think we're almost ready. So let's subtract the 4 from both sides. And this is the challenge. So I'm going to multiply both sides to solve for this by -3. And of course, now I'll have x here, but now look what I have to do. I have to reverse that direction because I multiply both sides by -3. Now I'm going to double check. You could try anything above -18. Let's try 0. What the heck? And we're good. And you would know right away, if you double check without having done this reversal, you would get the wrong answer here with the double check. And you would realize right away that you forgot to reverse the direction of the inequality. So while, you're not required to do double checks, I think it's a good idea because it would help you catch these kinds of mistakes. All right. Now we're ready for something else, something you're also probably familiar with, called binomial expressions. Now, binomial expression is formally defined as an expression that has two terms, but any exponents that we come across in this expression must be a whole number. Now remember, the whole numbers were 0, 1, 2, 3, 4. Okay, now also remember, x to the 0 power is 1. So that means constants count in this definition. So you must have constants. So we can have constants and powers of x, such as 1. Remember, so it constants and powers of x that are whole numbers. In other words, no negatives, no fractions. In other words, this doesn't work, this doesn't work. It has to be whole numbers, which means the constants implicitly are just x to the 0 power times that constant. X itself counts because it has an implicit exponent of 1. And that means other things like x squared, x cubed, etc. Those are all fine. And of course, ultimately, you must only have two terms. That's why it's called binomial. Anything else doesn't count as a binomial expression. Now, you'll see why this is so important in a second, but let's take a look at some examples of ones that these expressions are all binomial, and we're going to figure out why. All right, so, okay. And by the way, this is one, you can see now why when you learn these definitions, you see how easy it was to explain it when you know what a whole number is. If you were never introduced to the concept of whole number, it might not be so obvious what's going on here. So all these math terms that we've been learning and picking up, they start to pay for themselves, don't they? All that time you spent learning them, it's starting to become like an investment in your time. So anyway, let's look at these and see why they do in fact qualify as binomial. So we have constants in each one. And here, remember, this has an implied exponent of 1. So in each case, we have two terms. Constants are okay, or powers of x that are whole numbers. It doesn't matter, for example, if the number has a negative coefficient here. That's okay. The bottom line is that the exponents are 1, 2, and 3. Over here, by the way, you could actually rewrite this if you wanted to. It means the same thing. And you can see that all the x's have exponents that are whole numbers. Okay, so remember, any constant can be rewritten like this. And here there's an applied 1 for the exponent. So these all count as binomial expressions. And of course, there's only two terms. If I had 3x squared plus 2x plus 7, that doesn't count because it's got three terms in it. This has a different name. We'll see that later on. But it's not binomial. Well, does anyone want to look at this article? Look at this. They send me all these ads, like right in the middle of, okay, no, maybe we'll save this for later. Yeah. My computer is constantly sending me ads. All right. What about the cases that don't work? Save it for the non-existent spring break. I think you're right. That's what I'll do. I'll look at these places and say, wow, these wonderful places I would have gone if only I could. It's almost as good as actually going, isn't it? Yeah, I don't think so. Um, so we can only dream. So anyway, let's take a look at cases that do not qualify as binomial expressions, and let's try to figure out why. How about this first one? Now remember, 3 over x means 3x to the negative 1. So here, this does not work because 3 over x equals 3x to the minus 1. Minus 1 is not a whole number. Okay, remember, those are just 0, 1, 2, 3, et cetera, et cetera. Here are the same problem. Oh, negative 2 is not a whole number. That lets this one out. And down here, this 1/2, same problem. 0.5 is not a whole number. And while we're at it, why don't we recognize that something like this also wouldn't count, because this is x to the 1/2, and therefore this is not a whole number. Now this last one, the constant is okay, but there's only one term here. And that's why it doesn't count as a binomial expression, because it's only got the one term. It's a valid term, but there's only one. We need something else to go with it, besides another constant, I mean. Okay, now, the next slide I'm going to show you, it'll be like, imagine that somebody lived next door to you until you were, let's say, 14 years old, and you haven't seen them since. And all of a sudden they show up at your house one day for a visit, and you're going to be like, oh my God, it's you again. I haven't seen you in so long. It's the same idea. This is something you're all very familiar with, but it's probably been a while since you saw it or thought about it. But I guarantee you haven't forgotten it. All right, are we ready? We ready for this blast from the past? It's our old friend, FOIL. All right, FOIL, yes. How long has it been since you did any FOIL, applied FOIL to any expressions? And of course, you'll recall that FOIL means first. Oh, there it is right there. First, outer, inner, and last. Yes. Oh, use the box method. Yeah, you mean like this, like x plus 3, 2x minus 7. And is this what you mean? Like going across from left to right? No, there's another technique. Man, there's so many techniques out there. All right. Huh. I'm not sure if I ever learned the box method. This is what, like what this technique does. This technique that I'm showing you here, let's say you have x plus 3 and 2x minus 7. You're basically just going through them one pair at a time. You start here, multiply them out, then you go across here, box method. And if you go across here, you're multiplying negative 7 by x. And then you're going across this direction, which is 6x. And I've lined them up because they're both x's. Oh, yeah, I think you're right. It would be tough to explain it in English. And then here you've got 2x squared, and then you just add them up. I don't know if there's a name for this thing. The advantage of this approach is that you can have as many terms as you want, and it still works. The FOIL method only works for 2 binomial expressions. That's the only negative thing about it. It's restricted just to those cases. I've had this experience before with this class where people have been taught techniques that I never heard of, and they show it to me, and I think, wow, that is very interesting because it works, but I never thought about organizing it that way. Yeah, I don't think you can write on the screen, can you? I don't think so. That would be nice if you could draw a picture of it, but I don't think it's possible. because you're probably not the only ones who were taught that way. But you did learn FOIL, didn't you? I mean, even if you were taught the box method, you were. Okay, so let's stick with FOIL because I don't think everybody here knows, including me, knows the box method. Let's start with FOIL. The nice thing about FOIL is it's so easy. Okay, it really is pretty straightforward. I don't know who invented it, but they had a great idea. And if you notice too, when you have a word like this, where you are essentially you're creating it from abbreviations, it's called an acronym. Oh, there's so many technical words in English like that. Acronym, a word that is created basically by consolidating abbreviations like this. And there's a lot of words kicking around in English that we don't even realize any longer that they're acronyms, like, for example, laser. The word laser is an acronym. I don't remember exactly what it stands for. It's light amplified something, something, something. Watch this. Light amplification by stimulated emission of radiation. All right. We're going to keep calling it laser. How about that? No wonder they made an acronym out of it. Who would want to remember all that? Or how about this one? If you own a computer or any device like an iPhone or an iPad or anything, this word matters a great deal to you. What is this? It's not an animal with horns. Ooh, what is that all about? Oh my, you don't know? In this young generation, that's it, perfect. And it represents how much storage you have. So if you've got an enormous hard drive, 1 TB, for example, 1 terabyte, that's 1 trillion bytes of RAM. And each byte represents the storage of a single character, letter, or number. So you've got 1 trillion bytes of storage on your hard drive, but it's measured, it's called RAM, random access memory, because you can go get it whenever you need it. Now, the computer's operating system is stored in something called ROM, read-only memory, which you may not change. It's permanently written into the computer to make it run. If you accidentally change your ROM, you would never be able to use the computer again. So these are also acronyms that obviously play a very major role in our daily lives, don't they? But anyway, let's go back and revisit our old friend FOIL. So these are clearly 2 binomial expressions. How do you know? Because we have 2 constants and 2 x's, and that's it. We can multiply them together with FOIL by doing the following. Basically, you just have to remember what's what. All right, so you can do a little graph if you want. First is these guys. This is outer. This is inner. And then these 2 are last. Okay, so I hope you were able to follow it. It's kind of small. First is the first expression, first term in each expression, the 2 x's. Outer is the first and the last. Inner is the second, the last and the first. And then last is the 2 last terms, okay? And then when you're done, you can consolidate these 2. And what you end up with is that this is x squared plus x minus 12. They both are the same thing. And by the way, this is a binomial expression. But when you introduce an x squared, it becomes a quadratic expression. So the difference between the 2 is that in one of them we have an x squared. The other one, the binomial expression, can contain a term of x squared, but you can only have 2 terms in it. the quadratic expression has to have at least two terms, but it also, actually it doesn't, but it has to have an x squared in it. All right, so we put them together like you see here, and that's our final result, x squared plus x minus 12. Yeah. Now, if you want to use the box method, you can feel free to do so. I mean, the only thing, if this shows up in a test, it'll just say, oh, evaluate this expression or something like that. And you can feel free to use whatever technique you know. But I just think we should all be, comfortable with FOIL. If you still remember it, that's fantastic. If not, this is a great time to review it. If you've never seen it before, you can see that it's very straightforward. Well, having said all that, why don't we try the next one? There it is. Why don't you give that one a shot and see what happens?
Add the new Google widget right to your home screen and start your search fast. Just one tap and
All right. So just a little hint. Here's F. Here's O. Here's I. And here's L. All right. In case you forgot. All right. I think we should be ready by now. Let's see how you did. So again, this is F. O. You can see it written down here. I. And last. So 6x squared minus 10x minus 9x equal, and then we have 15 here. So we consolidate all these terms to come up with 6x squared minus 19x plus 15. And that's it. So these are equal to each other. All right. Is it all coming back? Yes, it is. Like I said, it's like your old friend that you haven't seen in 5 years. There you go. You're still friends. Okay. Oh, there's another one. Beautiful. All right. I think we use some practice. Why don't you go ahead and give this one a shot? After a few of these, you'll be really good at it. Don't worry. There's not that many different ones we could potentially have. All right. Let's see what we've got. All right. First is the product of these two, negative 8x squared. Outer would be negative 16x. Inner would be minus 4x, and then last would be a negative 8. So we bring these together. There we go. Look how easy that is. All right, good, beautiful. Now, we're building up to some heavy duty stuff now. This is going to provide our introduction to what we're going to call quadratic equations. So in general, a quadratic equation is written in the following form, and you can see we have an x squared term, we have an x, and we have a constant. We're setting it equal to 0. Now, a quadratic equation typically it appears in the form of what we call a parabola. And that means it crosses the horizontal axis twice. So that means there are two solutions. Sometimes they're called roots. And in other words, what this is saying is that there are two values of x. Oops. There are two values of x at which y equals 0. And that would be these 2 points right here. This is what we're searching for. The solutions, meaning the two x's at which the function has a value of 0. And so this curvy shape here, almost without fail, quadratic equation looks like this. It's known as a parabola. All right, now, just for the fun of it, we're going to do this. I don't remember if I've shown this website to you before or not. I use it all the time in my pre-calculus class. I just want to show you some specific examples of this, but I don't want to do it by hand because it's hard to do it by hand. There's this website out there, which you may or may not have encountered before. It's called Symbolab. And what it lets you do is solve equations, but it also lets you graph them. So if I write y equals, let's say, x squared plus 3x minus 7, it'll do several things, but it will let me draw a picture of it without having to do it myself. And you can see why, yes, indeed, it looks like what we expected. It is a parabola. It's facing up. And later on, eventually you'll learn how to find out where it reaches its minimum value. Right now, for today, what we want is to know where does it cross the axis. Now, they've already done that for us here, if you've noticed. Now, since I just randomly made this thing up, I've inadvertently chosen one with some pretty messy solutions. For example, here, one of the solutions, look at this, is -3 plus radical 37 over 2. And the other one is -3 minus radical 37 over 2. So it's some pretty interesting choices. So let's try another one. Well, maybe it'll work out more nicely. How about this? This one might be more promising. I just wanted the solutions to be nice integers. Ooh, I may have done it. No, God, no. Well, we'll get one. Don't worry. Now let's try this one though. What happens if I make this negative x squared? Let's try it. Oh, it's upside down. Oh my God. So yes, the thing about parabolas is that if the coefficient of x squared is positive, then it faces up. If it's negative, then it faces down, as you can see right here. Let me try a slightly different one here. There it is. That's more like what I was hoping for. And there's 2 points where it crosses the axis. They don't happen to be very pleasant numbers, but there they are. And so you can double check your work on this thing. Whenever you solve for a quadratic equation, if you're not sure, you can just go look at this Symbolab and say, oh yeah, there it is. It worked beautifully. But anyway, so that's what these quadratic equations actually look like. And remember, our job is to solve for the 2 values of x. Now, how do we do that, though? That's the challenge. There's really 2 basic ways of doing this. We'll start out with the first way is called factoring. The second is another of your old friends, the quadratic formula, which nobody forgets, the quadratic formula. All right. In fact, why don't I scroll down here and show it to you, and you'll say, oh my God, when was the last time I thought about this wonderful quadratic formula? Let's jump down here. As soon as you see it, you'll say, oh my God, where have you been? Oh, look at that. That's right. Oh, where has this been? You've forgotten all about your old friend, the quadratic formula. All right, minus b. Remember, you had to memorize this at some level. Minus b plus and minus the square root of b squared minus 4ac all over 2a. And that specifically refers to, I knew it. Most people never forget this one. There's something about it that maybe it's because they made you spend so much time memorizing it. You never forgot, did you? That's right. And this is, by the way, the letters. Yay, that's right, memories. Where would we be without memories? I mean, really. This is based on the setup ax squared plus bx plus c equals 0. So notice the b is the coefficient of x, the a is the coefficient of x squared, and the c is the constant. The other one that I find that nobody ever forgets is this one. Oh boy, there's our old buddy. Whose theorem is this again? What was that guy's name? Oh, you didn't forget, did you? See if I can draw that a little better. Pythagoras, that's right, our old buddy, it's the Pythagorean theorem. And what's the name of this side here? It has a special name. Starts with an H. Here we go. Hypotenuse, that's right. That's all right, you remembered it. That's what matters. You can always look up the spelling, hypotenuse. Yeah, this is a right triangle, which means what angle is that down there? Ooh, now I'm really digging deep into your memories. How many degrees are there in a right angle? 90, that's right. Oh, this stuff never disappears, does it? No. I'll tell you what, here's my challenge to you. At your retirement party, why don't you recite the quadratic formula for everybody, and they'll be so impressed. Okay. It's like, by the way, before we blow out the candles, I have to remind you, this is the quadratic formula. You see, I've still got it. If that's the case, why am I retiring? Okay. Well, anyway, but before we do this, we're going to go back and revisit this technique called factoring. Now, factoring only works well with certain cases, but it does work, okay? So you'll find that it works for some situations, but the nice thing about the quadratic formula is that it always works. And in my opinion, it's even quicker, but we do need to remind ourselves how to do factoring. The factoring works great for very well-behaved quadratic equations. In other words, especially if the coefficient of the x squared is 1. If not, factoring can get really, really messy. All right, so remember, now let's go look at Symbolab for a second and draw this graph, x squared minus 3x minus 4. As long as the technology is here, we may as well take advantage of it. X squared minus 3x minus 4. Whoops. All right. So we're going to scroll down. Whoop, no, not yet. We have to ask it for the graph. There it is. Now, the 2 points where it crosses are 4, 0, -1, 0. Okay, so it worked out very nicely. So we're going to confirm that by using our factoring. Okay, so how do we do that? Now, first things first. Basically, with factoring, you're essentially reversing the FOIL process. With the FOIL process, you already have two binary expressions or binomial expressions, which are multiplied together to give you the quadratic equation. But now we're working that backwards. So let me just show you. And again, this is something that you may have seen other techniques for, but this one works pretty well, I think. So let's give this one a shot. And you see, this looks very bizarre and abstract because these are letters, but if these are the factors, you can see why these factors would provide us with this quadratic equation, because based on FOIL, let's just quickly do the foiling up here. We have x squared, mx, nx, and finally we have nm. If you bring these together, you'll get x squared plus mx plus nx plus nm, which I can rewrite like this. Okay, so in other words, this is a constant of some kind multiplied by x, and this is another constant. Now, what this means then is that if I'm using the specific case of x squared minus 3x minus 4, what I'm looking for is two integers whose product is m plus n, and the same two integers have to have a product. Sorry, did I say that wrong? N plus m is -3. The sum is -3. The product is -4. All right, so again, for this specific case, whatever n and m are, they must be two integers whose sum is -3, but whose product is -4. It sounds like a puzzle, doesn't it? It does, a brain teaser. What are the two integers? And by the way, this will be unique. It's not the case that you'll be able to find two or more pairs of integers that satisfy these requirements. We have to figure out what they are. Okay, now how do we do that? All right, well, given that we know that those two things must be true, one thing you can do is this. Why don't we try this? Let's write out all the factors of -4. Okay, so we'll have 1 and -4, -1 and 4, 2 and -2. There's only the 4 of them. Of all of these, one of these must have a sum of -3. Which one is it? Oh, wow, that would be this one. Oh, what just happened? This one. So that means that n is 1 and m is -4. Now, how does that help us? Because remember, we're saying that all quadratic equations can be written as x squared plus n plus mx minus plus nm. Okay, that's the general form from up here somewhere. Yep. And then by plugging in these numbers, I can prove that this is true. The sum of these two is -1. Or we'll just write it as -x. And then this product is -4. Oh, sorry, no, it's not. It's 3. My fault. It's -3x plus, or -4 actually. And then I can set that equal to 0. Now, how does that help us? Because what I've basically just showed you is that x plus 1 times x minus 4 must equal the original equation, x squared minus 3x minus 4. And we can prove it with FOIL. All right, let's sneak that in here somewhere. So I'm going to FOIL these two factors, and we'll see that it gives us the right results. All right, so first, outer, inner, last. X squared minus 3x minus 4. So when all the dust settles, we say that these two terms are the factors of x squared minus 3x minus 4. All right, so now I know that was a lot. When you do this 2 or 3 more times, you'll say, oh, it's not hard at all. That was a bit much, I know, but when we do a few more, you'll say, oh, it's not that hard. It's just takes a little getting used to. But we did find what we were looking for. Now, one thing we do want to note here then when we're done is that we can take this one step further. Okay, if those are the factors, what are the solutions? Now, let's go back to Symbolab for a second. If you notice, it says here that the solutions are 4. Now, 4, 0 is that point where it crosses. The actual solution is considered to be that x value, which is 4. And over here, the solution is considered to be the x value, which is -1. Okay, so the solutions, meaning the points where it crosses, this parabola crosses the axis, are said to be 4 and -1. How would you derive that from here? What you would do is set this product equal to 0. And you would note, and this is the interesting part, that if that whole product equals 0, if either one of these is equal to 0, then this entire product would also be equal to 0. So there are 2 ways this can happen. X equals -1 and x is 4. All right, so in other words, we've just shown that the parabola crosses the horizontal axis where x equals -1 and +4. And we did that by factoring the quadratic equation, which was x squared minus 3x minus 4, and then using those factors to solve for the x's. All right, that's what this was all about. Ultimately, what we care about is the solutions. The factors are nice to know, but it's the solutions that we're really interested in. So let's do another one. If you've recovered from all of that, let's do another one. And like I said, it looks a lot worse than it really is. It's not nearly as complicated as it sounds at the moment. So let's try another one. And don't forget the Symbolab thing. It's just right there, symbolab.com. It gives you a lot of useful information here if you need it. But yeah, for our purposes, we just wanted to look at the graph. Look at all the stuff that it has. Does this tempt you to want to go on and take more advanced math classes just so you can learn about all this stuff? I bet it does. By the way, look at these ads over here. You know what happened over here? One day I was talking about symmetry in my statistics class. And I said, you know what's symmetrical is snowflakes. And so we looked at this picture of snowflakes, and now they want to sell me posters of snowflakes. You see how that works? They're pretty cool, aren't they? Maybe I'll buy it. Who knows? It is pretty cool. All right. Anyway, let's get back to this. So we double check with FOIL. Yes, we did that. We double check. Oh, you can also plug these into the original equation and make sure that they do in fact give you zeros. And so that's another way you can double check your results. But we've already seen that from the Symbolab, but still it's a good skill to have to be able to do this. All right, let's do another one. All right, so here we go. Now, what are we trying to do here? Here's the coefficient of x. It's -6. So whatever these two numbers are, they add up to -6. Their product is 8. Knowing this, what we're going to do is go through a list of all the factors. Now, by the way, when we first introduced the concept of factors, they were restricted to positives. Here we can use negatives. So in other words, this one will be 1 and 8, but it can also be -1 and -8. It can be 2 and 4, but it can also be -2 and -4. All we need is the pair whose sum is -6. Oh, look at right here. That tells me that x minus 2 times x minus 4 equals x squared minus 6x plus 8. Now, if all we wanted was the factors, we'd be done right now. But because we need the solutions, we now take this one step further and say, well, what do you know? How about this? It's x minus 2 times x minus 4 equals 0, or x minus 2 equals 0, x minus 4 equals 0, and that implies that x equals 2 and x equals 4. And those are my solutions. In other words, you have something like this going on. All right, now what we're going to do is confirm this in two different ways. We're going to plug these numbers into the original equation, and then we're going to look at Symbolab. Okay, so I'll give you a minute to catch up, and then we'll plug those two solutions into this equation. Make sure that both of them give us a 0, and then we'll take a peek at Symbolab. All right, let's do it. I think it's already here, actually. First, we double checked it with FOIL to make sure that those are indeed the right factors. But yeah, you can see when you consolidate these, it's x squared minus 6x plus 8, which is absolutely correct. Now that's done. Now we can confirm that the 2 and the 4 are indeed the solutions of this equation. All right. And how would you do that? Well, you just plug them into the original equation. In other words, you have x squared minus 6x plus 8 equals 0. Let's try x equals 2. Let's get that check out of there. All right, so yes, this one works. Then let's try it when x equals 4. You would have 4 squared minus 6 times 4 plus 8. 16 minus 24 plus 8. 0. Yeah, it works. We did it. It works because we know the FOIL tells us that those are the right factors and that the solutions we came up with, which are 2 and 4, do in fact cause this function to be equal to 0. All right, are we ready to prove it? Let's take a look at Symbolab. X squared minus, whoops. No, not that. Oh no, where did it go? That's right, I'll open up another one. All right, so we're ready. You notice how happy these people are. Of course they are, they're in math class. How could they not be happy? All right, anyway, so we got y equals x squared. By the way, if you're gonna use this thing on your own, don't leave out the y equals. It will not understand what you're doing if it's not listed as an equation. If you just write x squared minus 6x plus 8, it will not give you what you're looking for. I've discovered that by experience. Okay, just indulge it and make sure it says y equals this. And ta-da! And are the solutions 2 and 4? Let's find out. 4 and 2. Yes, we did it. Okay. And it is an upward sloping, it's facing up. In fact, when I was in high school, I had a teacher who referred to this as holding water. In other words, if you poured water into this thing, it wouldn't spill. But if you had the upside down one, it would not hold water. That's how we described it, holding water or not holding water. I don't know, it seems a little strange, but it works. Yes, if you had this device in your backyard and it started raining, it would hold the water. Okay. All right. Anyway. And of course, you can do all the double checks. Now, if you don't want to use factoring, or if it's a very complicated expression, then you're probably better off with a quadratic formula. Now, I did mention before that this is what all you have to do, but remember how this works. Those letters are the coefficients of the quadratic equation. So what if I had, now remember this one we had earlier. And we discovered, let's go back and remind ourselves what the solutions were. -1 and +4, all right? So we're just going to confirm that right now with our friend, the quadratic formula. So first things first, there's an implied 1 here. So that means A is 1, B is -3, and C is -4. You have to be careful of that. This 1, there's a 1 here. And so that's our A. The -3 is our B. And our C is -4. Now, in this formula, it's a fairly messy formula. You have to be careful, especially with the negatives. In my experience, when people make mistakes with this thing, it's almost invariably something to do with the negatives. The other thing, too, I want to point out here is that this expression has to be non-negative. If not, or b squared must be greater than or equal to 4ac. If not, you'll end up with a square root of a negative number, which of course means that it's an imaginary number. Now, in the real world, this could happen. But in this class, it is not going to happen. We're not going to have any cases where we have imaginary numbers. But in practice, it could happen that way. So just be aware that if you find a negative under that square root sign, you've probably made a mistake. All right. By the way, as always in math, there's a special fancy name for this expression. This square root, you may have heard of this before. If not, that's okay. This is just for the fun of it. This is referred to as the discriminant. Okay, there's always names for everything in math. A lot of them are Greek words. A lot of these math terms came from the Greeks. The ancient Greeks, like Pythagoras, invented a lot of what we know today as math. And so that's why a lot of the words have Greek origins. But anyway, let's get to it. Let's try this one. So remember, A is 1. Actually, let me do this. Just so you can see it more clearly, I'm going to copy the formula again onto the top. With a reminder that A is 1, B is -3, and C is -4. So here you can see all the numbers have been substituted in. And here we have negative, wait a minute. Sorry, I wrote this wrong. B is -3. That's right. A is 1, B is -3, C is -4. So here we have a -3, which becomes positive. Don't forget about that. Here we've got +9 minus a -16, which makes it positive. So when we're done with all these negatives, we've got 3, +3, plus or minus the square root of 25 over 2. Now, here we got a bit of a break because we have a perfect square in there. Also, don't forget what this thing means. Plus and minus means you add and subtract. It's like if you had, let's say, 3 plus and minus 4, that means you're actually taking 3 minus 4 and 3 plus 4, which means you have two numbers, -1 and +7. So that same thing is happening here. We reduce this to 3 plus or minus 5 over 2. So that's two things going on. 3 minus 5 and 3 plus 5, both are divided by 2. And that reduces nicely to our solutions, which we already knew, which are -1 and +4. All right. So again, you can see there's a lot of potential opportunities for making mistakes because of all those crummy negatives. All right. Just be careful. And again, if you have a negative square root, that's a sign that you've done something wrong as well. I will make sure that we do not have any situations like that in this class. Now, pre-calculus, we run into that all the time, but not here, okay? All right, now the next one, this is the second case we looked at earlier. We factored this one out and found it to be x equals 2 and x equals 4. But what I would like you to do now to get some practice is plug those numbers in. Now remember, here A is 1, B is -6, and C is 8. Why don't you go ahead and try your hand at this quadratic equation and make sure you come up with 2 and 4. All right. All right. Why don't you take a minute and make sure that happens? All right, so here's what you should have had. All right, so you plug in the numbers, and let's see. Again, watching out for those pesky negatives. You would have ended up eventually with positive 6 out in the front here. And inside the parenthesis, the square root, you have 36 minus 32. Oh, yeah, what do you know? Another perfect square. So we got kind of lucky there. And we've got 6 plus and minus 2 over 2, which we break it up into two pieces. 6 minus 2 over 2, 6 plus 2 over 2. Oh, you got it. Okay, good, good. So this time you already knew in advance what the answers were, and that's good. If something went wrong, you'll know it right away because you're not going to get your 2, 4. All right, now one last fun application here. Now, it may not look like it. Well, let's see. A carpenter is building a rectangular picnic table. Due to space restrictions, the length, which is down here, must be 2 feet more than the width. In order to build a picnic table with an area of 35 square feet, what must the dimensions be? So let's let the length be x, which implies, let's let width be x. This means this is x plus 2. All right. Now, we know that the total area must be 35. The area of a rectangle is x, it's the length times the width, which in this case would be x plus 2 times x, which is x squared plus 2x. And we want it to have a total area of 35. So therefore, what we have here is the following expression: x squared plus 2x must equal 35, which is the same thing as saying that x squared plus 2x rather minus 35 equals 0. And that means we're solving a quadratic equation to come up with our dimensions. So what I'd like you to do is take that quadratic equation and solve for it using our friend, the quadratic formula. All right. So why don't you give it a shot and take a minute and see what you come up with. And then we're going to see something interesting. That's for sure. All right. I don't want to rush you, but it's getting late. So we're going to go through all the steps here. And all right. So if you went through it, you'd see that you've got two solutions. Now, what's interesting about this particular problem, though, is that the x represents the width of a table, which means it can't be negative. So we can actually rule that one out. And it means that the actual solution to this problem is that the width is 5, which implies that the length, which if you recall is x plus 2, must be 7, and the area is therefore 5 times 7, which is 35. That means we've done it correctly. The carpenter has correctly set up this table to make sure that all the requirements have been met. The length is 2 greater than the width, and the total area is 35. And so we're able to do it with a quadratic equation with the understanding that this one, unless you're living in another dimension, this one is out. It has to be 5 feet. So you can see, what do you know? A cool application of the quadratic formula in the real world. Oh my God. All right, now, this is the end of chapter 6. So guess what? That means we're ready to do the chapter 6 problem set, which is on Moodle as we speak. So why don't you take that and download it, and then we'll work on that on Thursday, because we're ready. It's just as simple as that. So I think we're ready for the practice problems. I think there's only one right now. I might write a second one too, just to get more practice. We'll see how that goes. But right now there's one on Moodle waiting for you to download it. And so we'll go over that on Thursday, and then we'll be really experts in this area. All right. So other than that, I guess, unless there's last minute questions, I will see you all on Thursday.
All right. Bye. Thank you.
Th-
All right,
Thank
see you
you.
later.
Thank
Bye
you.
bye.
Bye.